All right, ladies and gentlemen, we are going to talk about orbital velocity and celestial motions in our next segment on video Earth science. So what we're going to talk about first of all is we're going to look at what you've already talked about a little bit about in the last lesson, and that has to do with angular diameter of objects. Okay, so the angular diameter of objects is dependent upon how close the object is to us and the object size. Now, two objects in the sky can appear to be the same size, but are very different. So, for example, the sun and the moon have approximately the same angular diameter, or apparent diameter. We call it apparent because that's what we apparently see. But the moon is only about a fourth the diameter of Earth, and the sun is 108 times the diameter of Earth. And the reason that they appear to be the same size is because the moon is closer and the sun is so far away. So the sun is 149.6 million kilometers away, and the moon is only 386,000 kilometers away. So the moon is much closer, so therefore they appear to be the same size in the sky, but they're very different because one is really far away and the other one is really close to us. And if you look at page 15 of your Earth Science reference tables, that's where your solar system data chart is, and that's where you're going to get all of your distances from Earth to the various objects. You're going to see their actual diameters, and you'll actually see their period of revolution, which is how long it takes them to go around the sun, and their period of rotation, which is how long it takes them to spin on one axis, which would basically be their day, the length of their day. So if you were on that planet, that would be the length of your day. Now, when we talk about apparent diameter, the moon's apparent diameter changes more than the sun. Okay? And that has to do with the moon having a greater eccentricity. When you have a low eccentricity, you're actually close to being a circle, and the more eccentric your orbit, the more oval shaped it is. All right, and remember that an ellipse is a mathematically defined oval, basically. All right, so then when we look at it, they have very similar angular diameters. All right, because the moon is closer to the sun and the sun is farther away. But the moons will change size more because the moon's orbit around the Earth is more elliptical or more eccentric than Earth's orbit around the sun. Now, so what is an ellipse? All right, so if we take a look at an ellipse, it is an oval shaped, but it's a mathematically defined oval shape. So in order to mathematically define an ellipse, what you have to have are these 2 points. Now these 2 points are what are known as foci. Now the important part of the foci is actually the distance between them. And then you're going to have one of the objects sit on the foci, one of the foci. The other foci is going to be an imaginary point out in space, and the other object will be, as in the Earth and the Moon, will be sitting on the and traveling along the outside of the ellipse. So in the instance of Earth and the Moon, Earth sits on one of the foci of the Moon's orbit, and the Moon travels around the ellipse. In the instance of Earth and the Sun sits on the foci, and the Earth travels around the outside of the ellipse. This all comes from Kepler's laws of planetary motion. Kepler actually mathematically defined the laws of planetary motion. There were 3 laws, and we'll talk about those. We'll get into a little archaeoastronomy later on, but this is the basics of planetary motion. Now, if we look at, and the reason that this happens, if we take a look, now you don't need to be able to calculate this formula, but if you look at Newton's formula for gravitational force, the force of gravity is dependent upon the mass of 2 objects and the distance between them. This g is a gravitational constant. All right, so that is a number you could actually look up It stays constant, and then this would be the mass of the first object, and this would be the mass of the second object, and then r stands for the distance between the two objects. Now, the gravitational attraction is actually influenced more by the distance between the two objects than the mass change. So, for example, if you doubled the mass, it wouldn't influence the gravitational attraction as much as doubling the distance. And the reason for that is because the distance is squared and you're dividing the masses multiplied. So, as distance between two objects doubles, the gravitational force reduces exponentially. All right, so let's take a look at how that works. Well, if we take a planet with a satellite going around it, anything that orbits another object is called that is the satellite of that object. And if we take a look at the distance here, you have the distance from the planet to the satellite when it's closest, and the distance from the planet to the satellite when it's farthest away. So you're going to have the same two objects, so therefore their masses will be the same, but their distance between them will change. So the gravitational attraction changes. Now, we'll call this R1 and we'll call this R2. Now, if we take a look at this, we use Newton's formula. Now, what we can do whenever we have a constant is you can just throw in the number 1, all right, so that you can see the relationship between the changes here. It's not the actual calculation of gravity by any means because the masses are not 1. But let's say we call the mass of each of these objects the same, and we have a mass of 1 for M1 and a mass of 1 for M2, and we're going to say that R2 or R squared is 1, right? So 1 times 1 is 1. So therefore, when you multiply this out, you're going to end up with a gravitational force of 1. And actually, the force that you would use is actually Newton's. But we're not going to get into those units either. That you'll deal with when you get to physics. So now, take a look at it. If we double the distance, right, we're going to use R2 here, all right, in our formula. And what we're going to do is we're going to say the mass of the object stays the same, but now we're going to double the distance between them, all right? And since you're doubling the distance and it's squared, what you're going to end up doing is dividing 1 by 4, or you'll get 1/4. So when you have the satellite here, you have a force of 1. Now when you double the distance, it changes exponentially. It drops to a quarter. So if you double the distance, it actually drops it to 1/4 of the gravitational attraction. Now, if we look at the eccentricity of an ellipse, all right, what we have is we're going to mathematically define our ellipse. So our ellipse has the distance between the foci, and so you have these two foci, and we're going to measure the distance between them, and you can measure this in miles, kilometers, centimeters, meters, whatever, because what happens is those units cancel out. As long as you use the same units to measure between the foci and the same units to measure the length of the major axis, all right, the major axis, and the major axis is if you draw a line through the foci to the extent of the ellipse, all the way to the very end here, and all the way to the very end over here. All right, so you're going to measure the length of the major axis and the distance between the foci. And when you divide this, you're going to end up with a number that's going to fall between 0 and 1. It is not going to be all the way to 0, and it's not going to be all the way to 1. So let's explore that. So if you take and you move these foci closer, right, this number gets smaller and smaller and smaller. And what happens if you take 0, all right, and you divide it by any number? What do you get? You're going to get 0, right? So the eccentricity of an object that has both foci at the same point is actually a circle, and you have an eccentricity of 0. If you take the foci now and you move them to the ends of the ellipse, you're going to have the focal distance be the same as the length of the major axis. So if you take 2 divided by 2, that's going to be equal to 1. So therefore, moving the foci, all right, changes the shape of the ellipse, and what happens is you end up with a number somewhere between 0 and 1. So if you do your calculations and you end up any kind of number that is greater than 1, you've done something wrong. You probably have got the numerator and denominator switched. All right, so what you got to do is you're going to take a look at this here. You're going to have the orbital velocity is going to be influenced by these two factors. You're going to have the shape of the ellipse, all right, and the eccentricity of the ellipse, and you're going to have gravity. Now, gravity is dependent upon the mass of two objects and the distance between them. So if we take a look here, you're going to have one foci, and let's say it's the sun. It sits on that one foci, and then the other foci is an imaginary point in space, and then Earth, we'll put the blue marble there, and we're going to have that travel around the outside of the ellipse. Now, as it travels around the outside of the ellipse, it actually changes in velocity. So its orbital speed will change as it goes around the ellipse. It's going to be slowest when it's farthest away, and it's going to be moving fastest when it's closest. Now, why is that? Well, if we go to Newton's laws, right, an object in motion will stay in motion until acted upon by an outside force. The outside force that's affecting this is gravity, and it's one object is pulling on the other objects. Actually, both objects are pulling on each other. So, believe it or not, both objects pull on each other, and as you come in closer, you go faster. And then what happens is you whip around, and the object wants to get away from the other object, but the gravitational attraction pulls it back in, and it whips it around again, and it whips it around again, and it whips it around again. And that's how an orbit happens. Now, one of the things that can happen is you could end up with what's called a degrading orbit, where it gets closer and closer, and eventually it's going to crash into it. Or you can have an expanding orbit, where it's going to eventually kind of move away from the other object.
Good grammar and spell important. But if you want...
There's a place where the space starts moving faster than light. So the light, which is trying to get out, it's rather like a kayaker trying to make their way upstream on a river that's going too fast.
At the center of a black hole, all equations break down. Even for physicists, what happens deep inside a black hole is a mystery.
We're in want of a new idea about how to explain what matter does at the center of a black hole. We're in need of a new law of physics.
Einstein himself concluded black holes were too strange to be real.
Albert never really liked the idea of black holes. He thought they were anathema. This was something that nature should avoid. The places where space and time became infinitely twisted up, he thought, no, nature shouldn't allow that.
Black holes are certainly odd beasts in the universe. They were thought to be peculiar, so peculiar as to perhaps not even really exist in the real world. Simply because your equations show that they can exist doesn't require that the real universe has them.
But over the years, suspicions rose. Stars were found behaving strangely, orbiting invisible objects, moving faster than expected.
Even though a black hole emits no light, is completely invisible, we know exactly what effect a black hole is going to have on its environment, on the stars in its vicinity, on the gas that wanders a little too close. So, will we ever see a black hole? No. But that's not what's important here. What's important here is we can see its paw print.
Suspicious that an enormous black hole was dominating the center of the Milky Way, Eric Becklin was eager to find its paw print. But even with infrared technology, when Becklin pointed the most powerful telescopes on Earth at his target, all he saw was this: just a blur.
The biggest obstacle that we had was the turbulence in our own Earth's atmosphere was blurring the images.
Even when the sky is clear, the gases in Earth's atmosphere are always on the move, distorting distant objects. To bring his view of the galactic center into focus, Becklin would need help. So he appealed to Andrea Ghez, an expert in dealing with the atmospheric blur.
The problems of the Earth's atmosphere is very much like the problem of looking for a penny at the bottom of a river that's moving, where the water is moving by very quickly. That motion of the water distorts your image of the penny. Just like the motion of the air in our atmosphere distorts our images of astronomical objects.
Gez agreed to take on the quest, to search for signs of a black hole at the center of the Milky Way.
A decade ago, you couldn't look at the center of our galaxy with high resolution, so you couldn't distinguish stars from one another.
Gez was able to correct the blurring effects of the atmosphere with a revolutionary new technology called adaptive optics.
So this little animation shows you the benefit of adaptive optics. You see the stars without adaptive optics, you turn the adaptive optics on, and all of a sudden you see stars. And in particular, you see stars near the center of the galaxy. Without adaptive optics, you would only see one big blob. And those stars are, in fact, the most important for us to track. We track all of them, but these are the ones that are the key to the problem. I mean, it doesn't hurt to take more.
Thanks to the new technology, the team could peer into the heart of the Milky Way with amazing precision.
Our view to the center of the galaxy is absolutely superb, and our ability to position stars at the center of the galaxy is like somebody in Los Angeles seeing somebody in New York be able to move their finger like this, okay, just 2 centimeters. That's the precision with which we can measure something that is 26,000 light years away from us.
Once the view was clear, Gez could start the hunt. If there were a black hole at the center of the galaxy, its paw print would be found in the rapid orbits of nearby stars.
Keep our fingers crossed.
The conclusive experiment to be done that really demonstrated there was a black hole was to follow the orbits of individual stars in the galactic center very, very accurately and with the highest precision possible.
When an object like a star approaches another, more massive object, the pull of gravity will make the star speed up. If it's orbiting close to a massive black hole, the star should accelerate to enormous speed and then whip around the black hole like a slingshot.
Okay, so we have the black hole here. The more massive it is, the more pull there is. The more pull there is, as it gets close to the black hole, the faster it goes. And we are measuring the speed of these stars. That's the key to getting the masses, measuring the speed of those stars.
To here, and so on.
As Gez continued to track the stars, she found some making dramatic hairpin turns.
It made a huge jump to over here. So it went all the way around. It's moving on order 10 million miles per hour. So it's just speeding away.
So what we see there is an experiment that actually shows them tracking the stars and demonstrating this concept of orbital velocity. Now, one of the questions that comes out of an experiment like this or a theory like this, when Kepler came out with it, is, if they're traveling at different speeds in their orbit. So when you're closer to the sun, you're going faster, and when you're farther away from the sun, you're going slower. And the seasons are influenced by our position with respect to the sun and the tilt of Earth on its axis. Well, wouldn't you have one season that's longer than the other? So what Kepler actually showed was that the reason we have the seasons the way we do has to do with the energy we receive from the sun. And that energy, if we look at it in units, energy units per square mile, you can take the area of these sweeps here, like this, and compare the area of the sweep here, and they will actually be equal. So an object, let's say it takes 1 month to sweep this, and it takes 1 month to sweep this because it's going faster. What you'll find is the area of these sectors is actually equal. So Kepler's other law of planetary motion is that the planets in equal time will sweep equal areas. So he has the two planetary motion, that an object travels faster when it's closer to another object. It's also whether it's in its own orbit or we're talking about planets as they move farther from the sun. So the planets that are farther from the sun will be moving slower than the planets closer to the sun. And they travel in elliptical orbits and they sweep equal areas in equal time. And those are the three laws that Kepler came up with, Kepler's laws of planetary motion. Now, because the moon has an elliptical orbit, it's going to affect Earth's surface. It's going to have changes on Earth's surface. Now, what are those changes going to be? Well, the changes are going to be the tides, because the moon pulls on the mass of the Earth, but it's also pulling on the mass of the oceans, the water. So what happens is you're going to have the cause of the tides have to do with Earth rotating on its axis, the moon orbiting Earth, and the moon's gravity pulling on the body of water on Earth. So the water on Earth's surface has mass, and the moon's gravitational force will pull on that water, and the sun also pulls on the oceans, but it's farther away, so it would influence it less. So if Earth had no moon, would we still have tides? And the answer is yes, but they would just be less drastic. They would just be less drastic. So when we look at this, the moon causes the tides to change, all right? So it causes the average tides to change depending on the position of the moon. All right, so during the full moon and the new moon, the high tides are higher and the low tides are lower. So the tidal range actually is greater when we have either a full moon or a new moon, and that has to do with the fact that the gravitational forces are in alignment. And if we look at the quarter moons, we actually have lower high tides and higher low tides, and that makes the tidal range less than normal. So therefore, it's due to the fact that the gravitational forces are offset at a right angle to one another. So if we take a look at this, we have the Earth, and then let's look at the new moon phase. All right, so we're going to put the moon here in between the sun and the Earth, and that's the new moon phase. And what we'll end up seeing is that the gravitational pull of the Earth, the moon, and the sun are all in alignment with one another. So therefore, by them being in alignment with one another, it's going to have a much more drastic pull on the water, so that when Earth rotates, it's going to cause the tidal levels to change. Now, from low tide to high tide is 6 hours. And a full cycle of tides from high tide to high tide or low tide to low tide, that's going to be 12 hours because the Earth rotates on its axis once in 24 hours. Now, if we take a look at the neap tides, what you'll end up having, with neap tides, you have the quarter moon, where the moon sits here, and this would actually be a first quarter. So you have the Earth, the sun, and the moon, and those forces are offset. Right? The forces are offset at a right angle. When you have the last quarter over here, it's the same thing, and you end up getting the gravitational pull of the moon pulling one way, the gravitational pull of the sun pulling another way, and therefore you're going to have different tidal level. You're going to have a much less drastic tide. So when you have the neap tides, you have a much higher low tide and a much lower high tide, and therefore the tidal range is much lower. All right, so now, if we take a look at the Earth Science reference tables, and this is the data chart in page 15, one of the things we're going to look at is the eccentricity of the orbit. And you guys commonly will hear in the news the supermoon. That has to do with when the moon is closer to the Earth. So when we take a look at the eccentricity of an object, when we say the orbit is closer to a circle, the eccentricity is going to be closer to 0. And when the orbit is most eccentric is actually when the eccentricity is closer to 1. So which one of these planets, if we look at eccentricity of orbit column right here, notice there's no units on it, and you're going to see the eccentricity, which one is more eccentric, which one is less eccentric, or which one's the most eccentric, which one's the least eccentric. So if we look at Venus, Venus is the closest to being a circle, so it is the least eccentric orbit. And if we take a look at Mercury, Mercury is closest to 1, so therefore it actually is the most eccentric orbit. So it has the most drastic change. If we take a look at Earth, Earth is very circular. It's not quite as much as Venus, but it is very circular. Now, if we take a look at the moon is actually a greater eccentricity. So the moon going around Earth is a greater eccentricity than Earth going around the sun. And that's the reason that the angular diameter of the moon changes much more drastically than the angular diameter of the sun. Now, if we take a look at how to calculate eccentricity, this is the chart off the front of your Earth Science reference tables, and the formula is right here, all right, and it has the distance between the foci and the length of the major axis. So if we take and we look at an ellipse, all right, and you have the two foci, and we're going to say a planet sits on one of the foci, the other foci is an imaginary point in space, and now we're going to have a moon going around that planet. And we're going to take and calculate it. So you have eccentricity is equal to, and I measured these, and you're going to have a 7 centimeter focal distance. So the distance between F1 and F2 is 7 centimeters. The distance of the major axis, remember, it's as if you draw a line between these guys, and you're going to measure from one end of the ellipse to the other right here, and you'll see that the length of the major axis was 9.6 centimeters. So therefore the eccentricity of this ellipse is 0.737. Now, eccentricity does not have units because they cancel out. Centimeters and centimeters cancel out. So you do not have any units here. Now, if we take a look at which orbit is more eccentric, the satellite of Earth or the Earth going around the sun, we take a look at Earth, it's 0.017. The satellite is 0.737. So therefore, if we take a look at this on the chart, we're going to see which orbit is closer to 0, which one is closer to 1. The one that's closer to 0 is Earth, so therefore that is the least eccentric, and the one that is closer to 1, the satellite, is more eccentric. Now, here's the link for Monster of the Milky Way. It actually does a good job of explaining a black hole the best they possibly can. And enjoy. Everything will be due on Monday. There's a quiz on Castle Learning, and there's also a review on Castle Learning, and you'll have a lab to do. If you have any questions, please ask.